Modern cybersecurity relies on the logic of Euclidean topology, a strategy of building rigid, two-dimensional perimeters to stop direct impacts. Threats are now dynamic. They probe and flow around these boundaries. When an adversary maps a network, binary filters that lack volumetric depth are easily bypassed by sheer volume and variance. The bubble daemon models security as a physical fluid environment. This approach replaces the static wall with a volumetric space where defenses wrap around data. Standard three-dimensional fluid dynamics fail to account for the energy leakage at the topological seams of higher dimensional overlaps. Mapping the system as a fractional dimension of 9.6 captures and measures the pressure within the 0.4 gap where information escapes. Analyzing this architecture requires a breakdown of the fractal pressure math, the obfuscation of 3D vector steganography, and the hardware-inscribed holistic code that manages the system's learning loop. Descending a node requires managing the thermodynamic pressure of the information flow rather than simply reinforcing a barrier. The equation F times G equals P total redefines force as the thermodynamic pressure of a superfluid vacuum. G is the medium's viscosity, and F is the displacement hole created by a mass. The surrounding fluid naturally pushes toward this localized low-pressure bubble to equalize the system. An adversarial interaction acts as an observer. In a liquid medium, a measurement probe creates a localized vortex. This interaction generates turbulence, shifting the data from standard 3D space into the 9.6-dimensional mapping. The golden ratio, phi, serves as the constant of flow and least resistance. Using phi as the base unit for the geometry corrects the errors found in linear maps and accounts for the seams between dimensions. To maintain equilibrium, energy must flow out of the vacuum at the same rate it pushes in. The toral flow model uses the reciprocal of the golden ratio to represent this simultaneous push and pull, ensuring the system remains stable. Aligning vector points at the golden angle of approximately 137.5 degrees prevents signal overlap. This irrational increment creates a perfect omnidirectional push that eliminates dead zones. Standard Euclidean geometry, built on 90 and 180-degree lines, cannot name these irrational vectors. They represent the points where the liquid vacuum reaches its highest density. Utilizing irrational scaling creates a stable liquid shell. The resulting defense is mathematically invisible to the linear measurement tools used by 3D observers. 3D vector steganography secures data by embedding it within the physical geometry of the signal flow. The vortex packet shredding mechanism breaks a message into 50 shreds and simultaneously generates 49 dummy ghost packets. These 99 points follow the irrational golden angle trajectories of a Fibonacci lattice. To an outside monitor, the transmission appears as the natural environmental noise of the network. These spatial coordinates are generated by feeding live phone sensor metadata, such as gyroscopic and accelerometer data, directly into the 3D engine. The particles act like spinning propellers tunneling through a fluid. The resulting hydrodynamic wakes create turbulence that destroys the temporal signature of the packet, making it invisible to standard topology mapping. A liquid code vortex shell wraps these shreds, masking their intent from network observers. By forcing data to behave like the natural entropy of the environment, the system achieves signal invisibility. The holistic fabric is a self-learning memory architecture that runs locally on the device, functioning without cloud compute or external models. This fabric is governed by the tension between a growth signal, or activator, and a limit signal, known as the inhibitor. Learning occurs through the continuous pressure between these two variables. Holographic etching weaves experience into the physical hardware array via pixel fragmentation. This process creates holographic persistence. The code retains its probability states and behavioral baselines even after a complete power cycle, because the data is physically etched into the state of the storage medium. The fabric acts as an immune layer. It compares every incoming event against the user sovereignty policy and adapts security boundaries in real time. Intelligence is an emergent physical state within the hardware, rather than a volatile software process. Adaptive systems risk chaotic drift, self-authorizing mutations that can compromise the security of the node. Maintaining stability requires a strict execution sequence. The math is refined, the engine is updated, the system is tested against datasets, and the architecture is improved. Variable independence tests prune redundant data points, ensuring the system only utilizes variables that provide measurable performance. The zero deletion policy prevents the system from overriding the core math. It can only add new layers of functional logic. The code is self-evolving, but never self-authorizing. Security is maintained through verifiable reproducibility. This architecture integrates fractal topology, 3D steganography for signal invisibility, and etched code for resilience. This resilience layer is platform agnostic, allowing ruggedized hardware like the Xcover 7 to operate as a sovereign node. Adversarial noise hitting the node is converted into internal system pressure. The attack itself provides the entropy required to trigger the system's learning cycle. The architecture turns the volume of adversarial data against the attacker, utilizing the external pressure of the network to insulate the node. This enables the detection of latent degradation from noisy sensor streams before a system failure occurs. Engineering an environment that converts adversarial noise into the fuel for its own evolutionary security creates a state of true digital sovereignty.